Welcome back, my friends, to another chapter in our little course on the COBOL programming language. Today we are going to look at data types in COBOL, so what kind of data types there are and how we can declare them in COBOL. Now we have 6 sections that we're going through today. First, we're going to look at elementary data types, so that's just variables holding a single number or a string. Then we look at so-called records, so these are data types that are composed of multiple of these elementary data types. We look at arrays or multi-arrays, which are called tables in COBOL. Then we will have a brief look at how we can format the output of certain data elements in COBOL. And finally, we are going to look at the basic arithmetic and string operations that are built into the COBOL language. Let's start with the elementary data types. In most programming languages, you can define variables anywhere in the code. So you can mix the program logic with definitions of variables. In COBOL, this is not possible. So here you have a very strict separation where you can declare variables and where your program logic is to be located. Namely, all the variables in COBOL have to be declared ahead of the program logic. They must be declared in the data division. And in COBOL jargon, we call variables data items, at least the elementary variables that just consist of a single number or string. And it is a bit unfortunate that COBOL uses its own terminology for practically anything. That sometimes makes it a bit hard to understand what is meant when you read COBOL documentation. But here, data items are used synonymously with elementary variables. Now, more precisely, this means we can define our variables that are processed at runtime in the working storage section. So recall we introduced that in the previous chapter when we went through the divisions. It's part of the data division. And other data structures that are to be read from files are defined in the file section. And we will cover file handling in a later chapter. So we will focus more on these working storage variables here. But the way you declare variables is the same in both cases. Variables in COBOL are traditionally global variables. That is, the whole program can see them, and a variable name has to be unique throughout the whole program. Otherwise, we will get an error. And the memory is reserved at the time when the program starts, so there's no dynamic memory allocation where you could create a variable later on and reserve memory for it. This has to be done when the program starts. It only makes sense to speak of local variables in COBOL when you're linking together several COBOL programs. So in this case, every variable that is defined in a particular module of the combined program is only visible within that module. And if you want to exchange data from one module to the others, you can do this via arguments that have to be defined in the linkage sections of the individual modules. And again, this is something we will talk about in a later chapter. Let's get right to it. Here we have a little example how to declare an elementary data item in COBOL. We're in the data division in the working storage section, and this line here declares a variable named name, which contains a string of 5 characters that contains the value hello. Let's look at the individual parts in this variable declaration. We begin with a 2-digit level number, which is 01 for elementary data items. Next up is just the name of the variable. So that is almost self-explanatory. This is how you will refer to this variable in your program. The next bit here, this keyword pic, or you could write it out as picture, the so-called picture clause. This indicates that you will afterwards declare the precise type of the variable. Then we have optional parts. These can be the keywords value, usage is, or you can omit the is, just write usage, and occurs. Here in this example we have value, which is used to initialize our variable with a value. So in this case it's a string hello. We don't have to do this, we could leave this out, and in that case we would have to assign a value to this variable later in the program logic, in the procedure division. Then there's the clause usage, or usage is. So this declares how the variable is to be interpreted by the program. For example, that is important for input and output. And it also influences how the variable is stored in memory. And there's the occurs clause. So this is used when you want to declare arrays. So for example, you could use occurs 10 to indicate that a variable is to be of a certain type is to repeat it 10 times. So that would define an array of fixed length. And we will get back to the occurs clause later when we discuss arrays, or tables as they're called in COBOL. We have to end the definition by a period, like almost everything in COBOL. The picture clause knows three basic types from which we can build up the data type of our variable. The first one is the alphabetic type. Here we use the symbol A. So these are strings of fixed length that may only contain white spaces and upper or lowercase letters. And for each letter that is allowed in our string, we have to follow the pic keyword by a symbol A. So if our string is supposed to have 4 letters, we have to use 4 times the letter A following pic. Then there's the alphanumeric type, which is a bit more general. So these are character arrays, again of fixed length, in which each character may assume any value of the underlying encoding. So usually this is ASCII, and in my examples I will always assume ASCII encoding. And again, similar to the case for the alphabetic type, every character that is allowed in our variable is indicated by a symbol X following pic. So if you want an alphanumeric string that is 5 characters long, we have to follow pic by 5 symbols X. And these are more flexible string data types if you want, because they can take anything that the alphabetic type can contain, but more. So this type X encompasses the type A, and therefore I will personally never use this alphabetic type in my programs. I will always use the alphanumeric type. And then there's the numeric type, or rather there are several different numeric types, as we will learn later. So these are just numbers that can be used for all sorts of computations, and other than the previous ones, which we cannot use for computations. And here, instead of A or X, we use the symbol 9 for each decimal digit that is occurring in this number. By default, the numbers are unsigned, and if we want to have a signed number, we have to precede our sequence of symbols 9 with the letter S. So this is for sign. And if we want to compute with fractions, then we can insert a symbol V, a small v or a capital V, it doesn't matter, at the position where the decimal point should be. All the symbols 9 preceding the V will indicate the decimal positions greater than 1, and all the symbols 9 following the V will indicate the decimal positions smaller than 1. Now here we have a first example, so data division in the working storage section. Here we have our level number, that's 0, 1 for all our data items. We have text, which is defined by the letter A. We have an alphanumeric variable, which is defined by the letter x. And then we have 3 numbers. So here we have an integer with 4 decimal digits. Here we have a signed integer, again with 4 decimal digits, but a sign. And finally we have an unsigned fraction, 4 decimal digits greater than or equal to 1. Here we have a decimal point and we have 2 positions after the decimal point. We can use a different notation for variables with many characters because it might be too tedious to always type out the a's or the x's for every character that should appear in our variable. So we can just use a number following the type a, x or 9 to indicate how many characters or digits our variable should belong. So an means we have an alphabetic string with n entries, but of course for n we actually have to substitute a fixed number in our COBOL code. We cannot let this depend on a variable because, as I said in the beginning, all the memory has to be allocated before the program starts. Here I have some more examples. We have text declared with repeating a's, and here we have text declared in this manner. So A10, this means we have an alphabetic string that's 10 characters long. And similarly, I've done this here for an alphanumeric string and for a second integer that now has 6 decimal places. I've changed my signed integer to have 6 decimal places, and yeah, have my fraction, and now I also included a signed fraction here. Let's try this out. So you see here I prepared these variables and I already initialized them with certain values by using the value clause following the picture clause. Variable text1, for example, is initialized with a string abcd. Our 10-digit or 10-character string text2 is initialized with hello world. And you see I left out the space because if I had the space in there, it wouldn't fit into the 10-character boundary anymore. And yeah, similarly, I have some alphanumeric strings here, so these can also take numbers, unlike the alphabetic ones here. And here are the numbers that I assigned some values to: integer 1, integer 2. So these are just some arbitrary values I assigned to them. Here I can use a sign, which I couldn't use in the previous one. And my fractions here, where I use the dot or the decimal point to indicate the fractional part. Let's compile this now using the usual command copc -x standard equal to IBM, and this is our program data types .cop. We have nothing in the procedure division, so obviously nothing happens here on output. So let's just include some code to print out these variables here. So this should print our first variable, so we expect to see this string here on output. And we can do the same thing for the other variables. Here I just copied it for all the other variables, and we will see what COBOL makes of this. Yeah, so here we get our first taste of COBOL printing out values of variables, and it's a bit odd when you look at the numerical variables. So the string variables look exactly like we would expect them. It's just the strings we defined over here. But when we get to the numbers, we see the following. So here we have, for example, with signed 1, we have a 6-digit number with a sign, and we assign it a negative value which is 4 decimal digits long. So we see that because it's defined as a 6-digit value, COBOL prints 6 digits and the leading digits are just set to be 0. So leading zeros are not omitted. And weirdly enough, the minus sign, because it's a negative value, is printed on the right of our value here. Then we have the fraction, which was 2345.98. And we see this is printed here, but without the decimal point. So it's quite confusing because just from this output we can't even see that this is a fraction. And weirdly enough, this is intended behavior from COBOL. And we will see later how we can fix these formatting issues for COBOL numerical variables, because COBOL gives you quite a few features that you can use to format how numbers are displayed when you print them. But there are some caveats to that, and we will see in a few minutes how that goes. If you recall that in COBOL philosophy, we want to assume that the people who read or write the program are not too tech savvy, so we would not want them to have to understand how the data is stored internally and how much memory is occupied by our data items. But of course, unfortunately, sometimes we do have to concern ourselves with the internal representation of data items. For example, if we want to pass parameters to an external C function that we link together with our COBOL program. In that case, we would have to understand how many bytes our data occupies in order to map it to the corresponding C data types. At least we can rely on the fact that an alphanumeric data item that's declared by the picture clause with xn consists of precisely n bytes. So every x precisely corresponds to 1 byte. So that's good to know. That's something reliable. And in principle, we can, with the alphanumeric type, use this to store arbitrary binary data in such an alphanumeric data item. However, COBOL does not make it too easy for you. First, you cannot use this alphanumeric data type for arithmetic. So even though you could store arbitrary data in there, you can't do computations with it. And you must give the content of an alphanumeric data item as a string. And as such, it is limited to printable characters. Now, the only exception to that is if you want to directly write the value of a byte in hexadecimal code, which you can do. But if you do that, you can only write a single byte in your whole alphanumeric data item, even if it is larger than just 1 byte. Now, hex values in COBOL are written like this. You have a preceding x, then you have quotation marks, and then the hex value for your byte within these quotation marks. And a value like that can be assigned to an alphanumeric variable. But for example, if we use something like this, where we want to assign 2 bytes in hex notation, that would cause an error. So it is a bit annoying. A workaround for this is you can use arrays that consist of single byte entries and then assign a hex value to each single byte in turn. Now this is a bit annoying to do, but it is something that works. And it's also possible to initialize an alphanumeric data item with 0 bytes. So do not confuse this with the character 0. So that's the printable character 0 is not the 0 byte. And you can initialize the full string with all 0 bytes by using the clause value low values. And in GnuCOBOL you can observe that this is actually done by default. If you do not use the value clause at all, so you leave the variable uninitialized, then GnuCOBOL will implicitly initialize it with zeros, but this is not an official behavior, so it's probably not something you should rely on, and you cannot be sure that other COBOL compilers would handle it the same way. Let's try this out with the byte field. So how do we do that? I declare an array. This is done as follows. So I just declare the array name on level 1, and then on level 2 or any lower level, I declare the individual bytes. So each of these bytes in byte field has just one X, so it consists of a single byte, but let's say it has length 6, so it occurs 6 times. Now here we have an array that's called array, whose entries are called byte field 1 to 6. And to these I can assign hexadecimal values using the move command. And this is how you address the individual entries in an array. So here I just copied several values to this byte field, and I use the hex notation to set every single individual byte. So this would be a way how you can have some data string to which you assign arbitrary byte values. And let's see how COBOL likes this. Should probably include the display at the end. And because I want to print all of them at once, so I'm not saying print byte field, which would be ambiguous because I wouldn't specify which one of them. I just print the whole array. That's why I give the variable array here when I want to print the byte field. Yeah, you see we get the same output as before, and now we get byte field and some weird stuff because I assigned some values to it that were not all printable characters. So that's why you get this weird output. For example, 0A, that's actually the new line character. So that's why we have a line break here. And we get this character E, which corresponds to hex 65 on the new line. So here you see it does work quite well. You can assign arbitrary values to the elements of a byte field, but the way you go about it is a bit complicated in COBOL. So I said before that we have different kinds of arithmetic data, of number types in COBOL. So that means if we declare some data items with 9 followed by the number of digits, then it's not immediately clear how much memory will be occupied by that, so what the internal representation is. Because each of the different numerical formats occupies different numbers of bytes for the digits here. And we can choose these different arithmetic formats via the usage clause, or usage is in the long form. Now we have the following. Usage display is the default format. So this is the format you want to choose if you want to print numbers on the screen. Here you have 1 byte used for every decimal digit, and the digit will just contain the ASCII value of that digit. So it's a bit of a waste of memory because your digits only range from 0 to 9. And the unfortunate thing is, in this display usage, COBOL will not allow you to perform all the arithmetic operations that you could have for numbers. Then there's usage binary. So here the numbers are just stored in the common binary format that you're probably used to from most other programming languages. So you just use the digits in a byte to encode a binary number, and that's what's used here to store the value. And the number of bytes that are reserved for the decimal digits here, that depends on the COBOL implementation. So here we're following the IBM COBOL standards, and this one requires 2 bytes if you have up to 4 decimal digits, 4 bytes if you have 5 to 9 decimal digits, and 8 bytes from 10 to 18 decimal digits. And you can infer from this that you're not supposed to use numbers in the binary format that have more than 18 decimal digits. Then there's usage computational, or just comp, where we have different subtypes. So comp 1 to 4, where comp 1 and comp 2 are floating point numbers. So comp 1 being a 4-byte floating point numbers, and comp 2 being an 8-byte floating point numbers, or a double as it's often called. And these two are rather late additions to the COBOL language. And note that if you use comp 1 or comp 2, you will not have to use a picture clause, so this pic keyword, when you define the variables, because for floating point numbers the sizes are standardized to 4 or 8, so it will always be clear how large that variable will be. So there's no need for a picture clause. Comp 3, or also known as the packed decimal format. So instead of comp 3, you could also write usage packed decimal. This is used for fixed point arithmetic. So here 1 byte is used to store 2 decimal digits in the picture clause. So 4 bits in 1 byte each encode 1 decimal digit. So it's a bit more efficient than just using a single byte for a digit. And then we have comp 4, which is just synonymous with the binary usage here. Other COBOL standards and compilers allow even more computational types, comp 5, comp 6 maybe, but that depends on the standard you're using. And also note the keyword usage can actually be omitted. So you could, instead of usage display or usage is display, you could just write display or binary after the picture clause. But you have to decide for yourself if you consider that to be more readable. Like so many things in COBOL, that's your choice. So here we have some more variables, and I included the usage clauses now, and also some floating point numbers here. So let's take a look at this. So I just copied over the slightly modified variables. So here I have a third integer, integer 3, with usage comp 3. So this is a packed decimal one. Integer 2 has now been declared to be usage binary. So before I didn't have usage, so it was by default usage display. Haven't changed anything for the signed integer. So I don't use a usage clause here, so implicitly it will be supposed to be display. Here I have my fractions, and finally I introduced 2 floating point numbers, float 1 and float 2. And I will include those in our display down here. And actually, let's make this one a negative, just for the fun of it, and see what happens. Yeah, so not much has changed up here. So the strings are just printed out just as before. Same for our integers. Even though integer 2 has gotten a leading 0 now. So I assume that comes from the bytes that are reserved for this data type. If we change the usage to computational 3 rather than display, our signed integer is displayed in the same way as before. So is our fraction without the decimal point, quite misleading. The signed fraction as well, with the weird sign on the right hand side. Now at least our floating point numbers seem to be displayed in a reasonable manner, so we do have the decimal point shown here, and we have the sign displayed on the left. Now what's a bit odd is that you already get some rounding errors here, despite us not having done anything with these variables. But yeah, instead of having 5.4, you see we have 5.39999, and instead of having 5.6 here, we have 5.601. Okay, so that's a weird properties of the floating point numbers. It might also be worthwhile to have a look how GnuCOBOL handles all of these data types internally, because as you might recall, GnuCOBOL actually generates C code out of the COBOL code and then compiles the C code, and that is what gives us our binary program. So we can explicitly look at the C code by just using the transpiler with the -C flag. Now what happens is that the transpiler generates 3 new files: datatypes.c.h, datatypes.c.l.h, and datatypes.c from our original COBOL source code. And this is the C program that corresponds to our COBOL program, so it looks a bit messy. And yeah, let's explore these individual files. So maybe let's start with the .c.lh. So the L stands for local, which is a bit misleading, because as I said before, there aren't really local variables in a COBOL program. But if we think about it as a module in a program that might be composed of multiple COBOL programs, then this header file .l.h contains the variables from the data division of our program. And yeah, there's a lot of stuff defined here. And here, data storage. In this part, we actually have the variables defined in our working storage section. The comments behind them indicate which variable is defined here. So you see every variable is defined as an array of this COB-U8 type. So I guess it's for COBOL unsigned 8 bits. So it's just a byte. So all variables are defined as byte arrays. And you see here the different sizes that are reserved. For example, for the 2 floating point numbers, we see 4 and 8. That's consistent with what we said before. The comp1 type is 4 bytes. The comp2 type is 8 bytes. And yeah, here you see the different different types of variables. And down here we have some additional information that's being stored. So a COB field. I don't really know what that is, to be honest. It's procedure parameters. Okay. So that might be some auxiliary information that is used if you pass variables from one COBOL module to another. I don't know. And these A values here are actually defined in the other header files. The COBS data types.c.h. Yeah, this is where they are defined. So some attributes for our data, I assume. And in this header file you also have constants that are used in our COBOL program. So you see here, these are all the variable names, but with the equal sign behind them. So this is what I used in the display instructions. So these strings that are used here to make for a pretty output, they are predefined here. And then we have these ones here. These are actually the strings that are used to assign the values to the floating point numbers. That is a bit odd, but COBOL probably knows what it's doing. And finally, here down here we have a short procedure that is simply, if you work through it, intended to reverse the byte order of a 16-bit value. I suppose this is somehow used internally by COBOL. And now let's have a look at how the COBOL program turns out in the C code. So here you have all kinds of initializing definitions and code. You can already guess that this has a rather involved runtime environment for COBOL. Here, where we have the comment procedure division, this is where actually the program logic starts. So we have a nice go-to that jumps to the beginning of our COBOL code, and conveniently every line of COBOL code is given here again by a C comment, and we have the corresponding C function. So the display in COBOL, we have this COB display C function that does that. We hand over some parameters, so I assume C1 F17, so I guess C1 is, this constant here, so this is the string. If you look here, first I output this string followed by the variable text1, so C1 is this string here. That's handed as the first parameter, and then F17. I suppose that's this additional information for our text1 variable. So here we define the text1 variable as a byte array, and here we have this this wrapping data type F17 with some additional stuff in it, and this we hand over to the display function. That's all we do. Then we have the move instructions for our byte array later on. So here we just address the individual bytes and assign the values, and finally we display that. And then there's a stop run and some cleaning up code. And finally, after that, we have all the initialization code. So this somewhat oddly comes only after the program logic. So here, this is all the code that sets the memory for our variables here that we initialized with some values already. So these are all these mem copies, and here we actually use the byte swap thing. So I guess this has to do with how the IBM COBOL standard represents data. I'm not quite sure. Yeah, and that's about it, I assume. Here we have an init function. That's probably for the runtime, not exactly related to our program logic. So if you want to explore this further, you can of course do this yourself by running this command here and looking at the C code. We've seen that COBOL is rather weird when it prints numerical values. So it puts the minus sign on the right of the numbers. It doesn't show the decimal points, and it shows leading zeros that are not really necessary. Why does COBOL do this? I cannot possibly tell you. At some point, someone must have thought it's a good idea to have these weird outputs and leave it to the programmer to format the numbers and the output format for him or herself. Maybe there's some method to that madness, and if you know it, then please feel free to write it in the comments. But I can't really explain why COBOL does it. Nevertheless, COBOL does give us some symbols and modifiers for the picture clause that allow us to control the format of the display and to make it more pleasant. Sadly, these additional modifiers just work for usage display, so not for the binary or the computational usages of numbers. In particular, this means if we want to properly print any variable that's defined as usage display or usage computational, then we need to have a matching variable of type usage display and move the value to that one and print this corresponding variable if we want to have it properly formatted. That's a bit annoying, of course. Now, these additional symbols include a period, which we can use instead of the V to indicate the position of the decimal point. If we do that, then the decimal point will be printed. We can use the symbol Z instead of 9 for numbers with more than one decimal digit to suppress leading zeros in the output. But we need to have at least one 9 to the left of the decimal point. And we cannot use the letter Z after the decimal point. But at least, yeah, we can get rid of the leading zeros. And we can use minus or plus instead of the symbol 9 for the same effect as the Z, so it would suppress leading zeros. But we use this with signed numbers. So then we don't have to use the symbol S, so we can just use minus or plus to indicate that it is a signed number. And if we use plus, then the sign is always printed. Whereas if we use minus, only negative numbers get a sign. So the sign is not printed unless the number is negative. And we cannot use both in one expression. So we either replace the 9 symbols by all pluses, or we either replace them by all minuses. We cannot mix plus and minus here. And also, if we have very long numbers and we want to make them more readable, we can use the symbol B to insert between the symbol 9s to add a blank between decimal digits. Finally, we have the formatters sign leading and sign trailing at the end of the definition of a data item. And these tell us if the sign of the number should be printed on the left or on the right of that number. So here we have another example. So now we only have numbers in our example, and we want to see how COBOL handles that. So here we have again integer 1, and now as I said before, we need to have at least one symbol 9, but all the other decimal digits are indicated by a plus here, and for the signed 1 by a minus. I use the sign leading modifier to make sure that when I print signed 1, the minus sign will be on the left, not on the right, which would be the default, as we have seen. Yeah, so this is defined as before, a 6-digit binary number. So here just say binary without the usage clause, just to have it a bit shorter. And then there's sign 2, defined as a binary as before. I have my fractions again as packed decimals now, and I define more fractions by using the period for the decimal digit, and I use the plus sign to suppress leading zeros, but do print the sign. Finally, I have my 2 floating point numbers, but nothing has changed here. Now there's a bit of a weird thing here, that if we use plus or minus in the definition of the variable and we want to initialize it in the working storage section with a certain value, then we have to put this value in parentheses. So we have to give it as a string, even though this is not a string variable. If we would not do that, we would get an error. Now, as you see here, if we don't use the plus or minus, then we can just write the number as it is, not as a string. However, we can assign a value to these variables here later in the code, and there we do not have to give the value as a string. So this is something really odd. And yeah, there's a lot of implicit typecasting going on in COBOL when you move numerical data around between variables that have been defined as different arithmetic types. It can get quite confusing. Here's my next program, output format, and this one is a modification of the previous one where I only have numbers. So yeah, we've just seen that. Let's see what COBOL makes of this. And I already have the code all filled out down here, so I display all of them. Now you will see that this variable here, sfrac2, has not been initialized, so I will just have to move a value to it later. And yeah, why not make this a negative value? Probably makes it more interesting. Otherwise it would just be the same as frac2. And we will print all of them. Now, here we have the integers that were defined with usage is display, and now they actually print out rather neatly. So recall before we had the leading zeros still in it and the minus sign was on the right, and now because we've defined this with the minuses here that would suppress leading zeros and the additional modifier sign leading, we do not have leading zeros and the minus sign is on the left. And similarly here, so this is a 6-digit number which only has 4 digits with its initial value. But since we used the plus here, instead of the 9s to define it, we do not show the leading zeros. Now here we have usage is binary, so these are numbers that are meant for computation, but not for printing. Yeah, so here all the leading zeros are shown, but at least by default the minus sign is printed on the left. Then we have fractions, the packed decimals, computational 3. And yeah, here the output is again a bit ugly. because we use the V to indicate the decimal point. That means the decimal point is not printed, which we can't do with the COM3 type because only the display type allows us to use the dot, as we use here in the later example. Here we have fractions with usage as display, so fractions that are meant to be displayed on the screen. I have to assign the value as a string, otherwise I would get an error. And yeah, these are actually nicely printed. So we have no leading zeros, and the decimal point is indeed printed as a point. And for the negative one, whose value I only assigned down here, we do not have the leading zeros either, and the minus sign is on the left. So this one looks good. And as before, the floating point numbers are already printed in the format that we would expect it to have. Maybe let's see if I change this to a number. As I said, I would expect to get a compiler error now. Yeah, so if I try to hand the value as a number and not as a string to a variable defined as display with the plus or the minus, then I get an error. Let's see if this makes a difference. No. Now observe one thing that is a little bit odd. We should have the sign displayed here because originally I defined it as plus plus plus, and this should always display the sign. But indeed GnuCOBOL suppresses it here, so yeah, at that point, maybe the implementation in GnuCOBOL is not fully compatible with the COBOL language standard. So the plus 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 here behaves exactly like a minus minus minus. But yeah, it's probably not too bad. Let's play around maybe with sign trailing. No, that doesn't do anything for this one, which is interesting enough. So the sign will not be displayed if it's positive. And yeah, even if we make it negative, there will not be a trailing sign. So apparently this is not properly implemented in GnuCOBOL either. But anyway, that's not really a bad thing. We get reasonable formatting here with these pluses and the decimal point, so that's good. And I can hardly think of a situation where we would want to have a trailing minus sign anyway. That's it for elementary data items, and now we are going to talk about records, which are complex data structures composed out of several elementary data items. In practically any programming language, we can define advanced data structures or complex data structures by combining elementary data items to yield the individual attributes of the complex data structure. Here we will call such advanced data structures records, and they are similar to structs in C, but with a crucial difference that in COBOL these structures are singletons. That means the definition of one such record defines a single variable. This is unlike C, where we could create different instances of a struct, but in COBOL we cannot create multiple instances of one and the same record unless we collect them in an array. So we could define a record and then using the occurs keyword have a record of this type, but that is of course different from being able to arbitrarily create new instances of a data structure as we could do in C. The structure of a record is given by different levels, where we begin on the top level 0, 1 in column 8, just like we did with the elementary data items. And this entry just contains the name of the record followed by a period. So there's no data defined on this line. It's just the name of the record. On subsequent levels, which can range from 02 to 49, we can either define elementary data items, so the attributes of our record, which we would define just like we did before, only with higher level numbers, or we could actually introduce the names of nested subrecords. So we can define a record within a record on a higher level number then. There are 3 special level numbers. The first one being level number 77, which is reserved for elementary data items and can be used instead of level 01, but I would not recommend it to avoid confusion, and I will never use level number 77. And then there are also level numbers 66 and 88, which are reserved for special purposes, and we will look at those two in a few moments. Now here we have our first example of a COBOL record. As expected, it's defined in the data division working storage section. We have the record name on level 01, and as mentioned before, there's no further data defined after that. And then on level 5, we have one elementary data item called Y, which is just an alphanumeric string with up to 10 characters, and we initialize it with the string data. And then we have 2 data pieces which are subrecords. So the record here has these 2 subrecords as attributes. So the first one is just very creatively called subrecord 1. The second one is called subrecord 2. And those 2 again comprise 2 elementary data items, x1, x2, and x1, x2, x3 in the case of subrecord 2. And yeah, just like elementary data items, we can or cannot initialize them, and we have all the options available of defining these attributes that we had as with the elementary data items. Now the names of the records on level 1 must be unique, obviously, because all variables are global, but the name of data items in subrecords must only be unique within those subrecords. For example, you may spot that we have x1, x2 in subrecord 1 and x1, x2 in subrecord 2. And this is allowed because they are, if you like, hidden within those subrecords. How would we address those non-unique names within different subrecords? We can use the in qualifier for that, or equivalently the off qualifier, so those two mean exactly the same. So for example, if we want to address this data item x1 here, we would refer to it as x1 in subrecord 2 of record name. And you would only have to dereference this up to the point where x1 would become unique. So this last bit is actually redundant, because as soon as you have x1 in subrecord 2, you would know that it has to be this particular x1. And for example, this variable y here, because it's globally unique, we could even address it directly without using this in or off qualifier. And here mixed in and off, just to make it a bit more appealing, not too boring with having in, but this could be also the keyword in, or this could be the keyword off. Those two are completely interchangeable. And here we have this record in our COBOL editor, and we will do a few things with it. For example, we can move some data into some of its entries here. For example, if I want to move something to this variable x1, which has not been initialized, I could do it like this. If I were to compile it like this, I would get an error because it wouldn't be clear if it's this or this x1. So maybe, let's actually verify this. Yeah, you see we get an error. X1 is ambiguous, needs qualification. So let's qualify it. X1 in sub record 1. Let's see if that is acceptable. Yes, it seems this is acceptable. So we only need to dereference x1 up to the next level at which it is unique. But maybe if you have a longer program, it might be nicer to do the full dereference like this. So then we know it's x1 contained in subrecord 1 of the record name. And yes, COBOL will accept this. That's good. And we can also move data to the numerical variable x1. So you see x1 here was an alphanumerical one. x1 here in subrecord 2 has to be a number, so we can because it's signed, let's give it a minus sign, and COBOL will accept this. Let's display these variables. Just to make sure everything works as expected. Oops. Yeah, so we get the output of these two variables that are both called x1 in the weird COBOL formatting. We don't care about the making it into a nice proper formatting right now. I'm just interested in properly accessing the entries in our record. Because this variable y is globally unique, so there's no other occurrence of any variable that's called y, we do not strictly have to dereference it with y in record name when we want to display it. See, that works. So y was already initialized, we don't need to move any value to it, and it gets output here. Again, maybe just for readability, it might be nicer to write it like this. Has the same effect, so there's no problem here if we write it with the in-record name or without the in-record name. And similarly, we could display this variable x3, which appears only in subrecord 2 and not in subrecord 1. So this is actually also globally unique, even though it's 2 levels down from the record name. So we do not have to dereference it, and yeah, it works. So here we assign a hex value, which actually prints in a question mark. And again, it's perfectly fine to write this more explicit. It makes no difference. So this is how you use records, how you define records, how you define nested records, and how you access the attributes within a record. Records can not only be defined in the working storage section and manipulated in the procedure division, but we can also read them from files and write them to files. And to do this, we have to define the record in the file section, not in the working storage section, which is also contained in the data division. To define a record that is to be read from a file, we must precede this by the symbol fd, followed by the name of a file descriptor. So we have the usual definition of a record, but even before the record name, we have the symbol fd and the name of a file descriptor. And then this file descriptor must previously have been assigned an actual file name on the disk in the environment division. So to make this clearer, here I have an example. First the environment division, then later the data division. In the environment division input-output section, file control paragraph, we define a file descriptor, so select file descriptor, that's the name of my file descriptor, assign to, and then some file name. And probably I forgot to put a period here. I would assume COBOL requires a period here. Then with this file descriptor defined, then in the data division, in the file section, we define our record as we would normally do, but we precede it with fd and the name of the file descriptor that is associated to this file. And so this tells COBOL that it expects the test file here to be filled with data that is built up from copies of this record. And then you could step by step read out different data sets which match this record structure. But I will not go into file handling here. This will be discussed in a later chapter. Now remember that we had the two special level numbers, 66 and 88. And I want to first explore what the level number 66 means. This can be used together with the renames clause to assign alternative names to a previously defined data item, or even a group of several consecutive data items within a record. And to combine several of such previously defined data items under a new name, we can use the keyword through, or its shorter American spelling is also allowed, together with the renames clause. Now this may seem abstract, so look at an example. So here we have in the working storage section a record which I call personnel record, and it has certain attributes that may refer to an employee. So we have first name, last name, street and city, we have the department and the salary. And now you would maybe want to access certain of these items together sometimes in a convenient way. So for example, if you want the full name, then instead of just reading out first name and last name individually, you could do the following. On level 66, you define full name as a renames for first name through last name. That means the data item full name now refers to the combination of first name and last name. So if you were to display full name, it would display both of these data items here from the personnel record. And if you, for example, want to have the full contact information for your employee. That's the name and the address. Then you could do this. Contact renames first name through city. So that would combine the first 4 entries in the personnel record, and then you would have the contact information for that employee, but you would omit department or salary because that's not relevant for the contact information. And you can just rename single data items, for example. You could rename org into the department, so the department where the person works could now be addressed just by the variable org. And you cannot apply the renames clause to data items defined on level number 66 or 77, or to the complete record. Let's look at the example for renames. So this is the same example I had on the slides just a moment ago. The personnel record, first name, last name, street, city, department, and salary. Here are the renames. And here's an example. It's always a nice example to use The Simpsons for fictitious employees. So here we have Homer Simpson working at the nuclear power plant in Springfield, and this might be his employee record. So we move Homer to first name, Simpson to last name, his address, 742 Evergreen Terrace to street, Springfield to city, 362.19 as his salary, and safety to his department. We can display different parts of this data structure, or rather this data structure filled with these items. We can display the personnel record as a whole, so that would print all of these entries here, and it would just print them one after another without any formatting. And we can rely on that all of these fields are 20 characters long, so that would give us a little bit of spacing to make it look decent, but it might not be the best idea to do that. Then we can print the full name by using this rename clause here to access first name and last name. So this will just print Homer Simpson. Then we can print the contact info by using this renames here. So this would just print the city and the street, or in the other way around, the street and the city. And finally, we can use org to just print the organization. Now let's see what this looks like. Compile. So the personnel record, the full record here gets printed. Then we print full name, which is this rename clause here. So it just prints Homer Simpson. Contact info, everything from first name to city. So the first 4 entries from our record. And finally, org is just a renaming of the department. So this will just print safety because that's where Homer Simpson works. Next, we want to explore the level number 88 and condition variables. Now, this is a little bit complicated maybe to understand, but let me motivate it by saying that there are no Boolean data types in COBOL, so no data type that would represent true and false, and there are no flags or switches in COBOL. But to remedy this a little bit, COBOL allows us to define so-called condition names that can be used for testing certain conditions. And sometimes this can be done quite conveniently, as we will see in the example. And to some degree, these can be used to emulate the behavior of Booleans or flags or switches. And these names, condition names, are implemented by defining a condition variable on any level 0 to 49, so the usual levels for data items, and then followed by condition names on level 88 and the values that these condition names represent. So this will be much clearer once we look at this example. Here our condition variable is population size, which is a number with 8 digits. We define this on level 1. Now this condition variable is a record, and to use it as a condition variable, we define the condition names here with level 88. So assume what we want to do here is we want to classify a settlement by its size into one of these categories. So if the size is 0, the population size is 0, then the value 0, then we consider it a ghost town. If it has between 1 and 9,999 inhabitants, we consider it a village. From 10,000 to just under 100,000, we consider it a town. And above 100,000, including 100,000, we consider it a city. So here we use the value clause with the through keyword to indicate a range of values. And if the range of values, if population size has a value in this range, then the village condition is true and the other conditions are false. So we must use this value keyword to indicate the values, and yeah, we can have a constant value here, or as I said, use through to define a full range. And we can use such a condition name in an if condition, for example. So here that was our example, and such an if condition would look something like that. If village, then do something that villagers would do. So if, let's say, population size has a value between 1 and 10,000, then the village condition would be true. So then this condition in here would evaluate to true, and we would execute whatever follows then. And that's of course much easier than taking a variable and checking if the value is within a certain range. And yeah, if conditions, we didn't talk about them too much. We will explore them in detail in a later chapter on program flow, but I think here it's self-explanatory how this would be used. A nice thing about these condition variables is that we cannot just set their class here by moving a numerical value to this variable, but we can also use the set operation to directly set population size to ghost town or to village or to either one of these conditions. For example, set town to true, then population size would be in the class town, and what that means is we would assign to population size the minimal value in the range that would classify it as a town. But yeah, this is a GnuCOBOL specific thing maybe. I'm not sure if other COBOL dialects or implementations would handle it in the same way. You would have to try that out. Let's look at the example for this now. So here we have our population size with ghost town, village town, and city, just as we defined it before. And now let's play around with this a little bit. Let's set city to true. And then we display population size. And we expect a value that corresponds to city. So as I said, it will be in GnuCOBOL the minimal value here. So we expect to see 100,000 as an output. Let's try this out. Yeah, you see we get 100,000 as an output, so the population size matches the number that is required to make it a city. Let's use it in an if condition. So if ghost town, then display 0. Yeah, COBOL if conditions are a bit picky when it comes to punctuation. So you do not use periods after the if or the else if, as long as further conditions will be included. Yeah, and I'm just typing out here what the minimum population would be for the respective conditions. Okay, now we have set population size to city, so ghost town, village and town will evaluate to false and city will evaluate to true. So first we will print the population size and then we will print this 100,000 plus attribute here. Yeah, that worked, and maybe let's change this to ghost town just for the fun of it. Check that it still works. Yeah, so population size is 0, also defined here as an 8-digit number. And here, because now the ghost town condition evaluates to true, we simply display 0 down here. And this is how you use level number 88 and conditional variables. And now we look at arrays in COBOL, which are called tables here. Recall that we observed earlier that any elementary data item or record in COBOL defines only a single instance of this type, and if we want to have multiple instances of the same type, then we have to use arrays or tables, as they're called in COBOL. So I already showed you an example of tables briefly in the byte array that we filled with hex values before, and now we want to explore this in more detail. To define a table, we first state the table name on level 01, and then the following level numbers that are strictly larger than 01 contain the definition of the table entries. Now we can have either elementary data items or records as table entries. If the table contains elementary data items only, then the next level contains the definition of this data item in the usual manner that we learned before, but followed by the occurs n clause, which states that this table contains n entries of the given type. And if the table consists of records of the same type, then the next level contains the name of the record, and now the name of the record is followed by the occurs n clause. And then after that, the subsequent levels define the structure of the record in the same manner we saw before. So here's an example of the two cases. Here we have what I call simple array. This is just an array that contains 1 byte characters, but 10 of them. So this is like a string containing 10 characters, if you like. And we define the name of the array on level 1, and on level 2 I define array entry as the entries with a picture clause x, just 1 character, 1 byte that occurs 10 times. Next, we have an array of records. So I call this personnel table, and here personnel record are the entries of this table, and we have, say, 30 of them. So this is the name of the record that is contained in the table. And yeah, we use the occurs clause after the record name, and then we have the entries in the record just as we would have it if we defined a single individual record. Now we can initialize tables with certain values. So the simplest way is just to use the value clause on the definition of the array entries. So as in this example, we have the array entries here, occurs 10, and use value 0. And this would cause all the entries in the table to be initialized with the same value that's given here. So all array entry would have the value 0 here. And we have another option to initialize an array if we do not want to initialize the whole array with the same value, but each entry with a different one. And here we have to use the value clause after the name of the array, so on level 1. And we have to put all the values for all the entries in the array consecutively into one string, which has to be enclosed in quotation marks, even if it's a numerical data type. And of course, this is convenient in theory, but it is actually not very practical when we use it with more complex data type, because then we would have to write all the data for all the entries just in one long string. It works for a very simple one like this, where each character in the string corresponds exactly to one of the repeating entries in our table. But if it would be any more complex, if we had, for example, numbers here with fractions and then writing all these after one another into a string here, that would be really messy. If we want to access the elements in a table, then we use the name of the table entries followed by the index n that we want to access in parentheses. And note, we do not use the name of the table itself, but the name of the table entries. And also note, indices in COBOL start at 1. They do not start at 0 as, for example, they would in C or in Java or many other languages. So here we have an example. Again, I have my simple array that I initialized just with these values 1, 2, 3, 4, 5 and so on. And if I just want to access the elements of this array, then I can use it like this: display array entry 1, display entry 5, display entry array entry 10. So these should output the first, the 5th and the 10th element of this array. And yeah, as I said, note, to do this we use the name of the array entry here, not the name of the table itself. Let's see how this works. So here we have a little file with our simple array that has been initialized. Now I initialized it actually with letters rather than numbers. That makes it maybe a bit clearer. And here's our personnel table with first name, last name, department, which occurs 30 times. And I want to see how we can access certain table elements. First, let us display a few of the array entries. Say array entry 1, array entry 5, array entry 10. So I would expect to see here A, D, no, E and J from these ones. Yeah, with the personnel table, we haven't really written any values to it, and you can immediately see if we were to initialize our personnel table with something like this, then we would have to have 30 entries in one string that correspond to, each of which corresponds to these 3 data items here, so that would be very, very impractical. Let's say we move some data to our personnel table, or actually I refer to the table, to the record within the table to assign the data. And of course, this is not what I want to do. I want to move a string to personnel record. First name in, oops, this is a bit, and let's see how that will work out. And I will also display personnel record 2, which should be empty, so I don't necessarily expect to see anything there. Let's compile it. Yeah, so we get what we expect. So we get array entry 1, 5, and 10. So A, E, and J from this simple array. I have assigned these values to the first entry of my personnel table, and I see them here. And I also print the second entry, but I haven't assigned any values to that one, so we get an empty line here, a blank line. We can define tables with multiple indices or multi-arrays by nesting tables into one another. And then we can access their elements by using multiple indices in parentheses in a straightforward way. So here I have an example. I have a matrix. So a matrix has rows and columns. So I have one table for the rows, and within that I nest another table for the columns. And that one contains the matrix entries, the actual data in the matrix. And in this case, I just take them to be fractions with 4 digits and 2 digits after the decimal point. And here I have an example of what we can do with this. So we can move some numbers to the matrix entries, and we do this by directly addressing the matrix entries with the double index notation. And then we can print the individual rows if we just use one index. So that would print for the chosen row this whole structure here. So the whole nested table would be printed in this case. And then we can print the matrix columns, or the entries rather, in the matrix columns with the double indices, and that would give us exactly the same as if we directly address the matrix entries here with a double index. I define the matrix just like I did on the slide. It's a 3x2 matrix, so we have 3 rows and 2 columns. And then down here we can actually write all these matrix entries and then access them and see what we get. Okay, so up here we got the same output as before with Homer Simpson and our simple array. Yeah, and as you can see, if I print matrix row 1, 2, or 3, then I get in the ugly non-formatted COBOL output, I get the data that I put in here. So row 1, I should get this entry here. And yeah, that matches these 2 entries here. In row 2, I should get this entry and this entry. This matches these two, and yeah, then row 3 should be those two, which matches this one here. And as I said, addressing the matrix column with a double index, so the second nested table with a double index, or the entries of the table themselves with a double index, that gives us the same output. So far we have only used constant numbers, constant values to address elements in a table. For example, when we write something like display array entry 5. But very often we will not know before executing a program which entries in a table we want to access. So what we would like to have is a variable that we can use for the index, so that we can compute an index dynamically. And this should work, of course, somewhere like this: display array entry index. So this would be our variable that contains the index we want to access. Now COBOL has two ways to do this, and they're at first glance maybe a bit confusing what the difference is, but hear me out. The first one is called subscripting, which is maybe the straightforward way that you would expect. You define some numerical variable in the working storage section and simply use that one as an index. That works. Then there's a second method called indexing. What we do here is we define a dedicated index variable for a table. So that's a separate data type, if you like. And these variables cannot be used for any other purpose. Now, the naming convention, subscripting and indexing here, is completely arbitrary and quite confusing, like so many things in the COBOL terminology, but you just have to memorize which one is which. Now, you might ask yourself, why does COBOL make this so complicated? Why can't we just go with the natural approach to use a numerical variable to address an index? Why do we have this weird indexing option? And there's actually a good reason for that, because if you think about what happens when we access a table element, then what happens is that the compiler has to generate code that computes the offset of this table element from the beginning of the table in memory. And to do that, if we were to use the subscripting method with some numerical variable, we would, for each index access of the table, have to convert the numerical data type that we use into a binary variable. So internally, the computer will use a binary number to compute the offset from the beginning of the table. So we have to convert our variable into binary. And that, if it's not a binary variable to begin with, that would be a bit of a lengthy conversion. And that would have to be repeated for every access to the table. So by having this second method, the indexing method with dedicated index variables, the compiler has the possibility to implement these index variables in the most efficient way to compute offsets in memory, and would not have to use any conversions when table entries are accessed. So indexing can therefore be much more efficient than subscripting. And in addition to that, several of the built-in COBOL functions for processing tables require the use of index variables. Now we have two ways to declare these dedicated index variables for accessing table elements. The first one is to declare an index variable by following the occurs clause with the keywords indexed by and then the name of the index variable. And if we do it this way, then the index is bound to the table in which we declare it. So we cannot use it for any other table. And the second way is to declare a variable in the working storage section without a picture clause. And the usage will be usage is index. So then we have, if you want, a generic index variable that we can use for any table we like. And we can use that to save temporary index values. And how these index variables are represented in memory is, of course, compiler dependent. They're not treated like normal data items, such as the ones we defined in the working storage section. And naturally, their names must be unique throughout a program. If we want to set the value of an index, we use the set instruction. So for example, if idx1 is our index variable, index1, then we can use the instruction set index1 to x. And here x is either an integer number or another index variable. Here we have an example of that. So again, our simple array here with its array entries, and we use the keyword indexed by idx, an index variable. So we can use this variable to address the entries of simple array. And before that, I declare another index variable, which I just call idx1, index1, with usage is index. And we could also use that one to address elements in our simple array. So here in the example, we have set index to 3 and then display array entry index. So we should get the letter C from that. And then I use set index1 to index and display array entry index 1. Then we should also get the letter C. Now, if we want to change the value of an index variable, we could either use set to set it to a different value, or we could just count it up and down by using the keywords up by or down by instead of to, and followed by the desired value that we want to add or subtract from the current index value. So let's see that in an example. What I've done here now is I introduced an index variable, index1, usage is index. I also used a binary variable, just a normal numerical variable with usage as binary that I call sub, which I will use for subscripting in the table elements. So that's also allowed, just using a normal variable, but this is the less efficient way. And what I changed here is I added this phrase here, indexed by idx, to my array entries. So this is the dedicated index variable that I can use to access entries in my simple array here. Now let's put these 3 indices to use. Let's begin with the index variable that was defined within our simple array. I just set it to 1, so we should get the letter A as output. Then I use my general index variable, index1, which I just set to the same value as index. So it's at this point it will also be set to 1. But now I can change the value. Let's say I add 2, I have set index 1 up by 2, so now it should have the value 3. So we should see the letter C if we print this. And yeah, just for the fun of it, we also, let's say we print the index variable. And I will use this subscripting variable, which is just a normal variable to begin with, to also access an array entry, namely here the entry 5, so I should see the letter E here. So expect to see A, C, and E. Yep, so this is just our output from what we wrote previously, and here We have the letter A when we address our table with the index IDX. Here we have the letter C when we move IDX to IDX1 and increase it by 2, so we have index 3 now. And indeed, that's the value of our index variable. And then we move 5 to our subscript variable and access the corresponding array element, which is the letter E here. So everything works as we would expect it. Recall that before we could use the level number 66 together with the renames clause to assign different names to groups of data items in a record. And we can do something similar with the redefines clause for tables that occupy the same size in memory. So we can have two tables that all together have the same size in bytes, but might have a different layout of rows and columns, if you like, or different number of indices that we use to access the elements. Now, let's look at this example here where we use this redefines to decrease the number of indices to address entries in a table. So here we just have our previous matrix record, or table to be precise. So we have a 3x2 matrix with 3 rows and 2 columns. And now if you think about it, if you take a matrix and you cut out all of its columns and just glue them together one over another or one behind another, you just get a very long vector. So we could see this matrix as a long vector with 6 entries, because we have 3 rows, 2 columns, that makes 6 entries in total. So we could think of it as a long vector with 6 entries. So I do this as follows. I declare long vector, redefines matrix, and then I just declare my vector entries as elements of the same type that occur 6 times. So these have to occur as many times as I would have total entries here in my matrix record. Now here I define my long vector as redefining matrix. Here the entries of my long vector. Insert this here, so we have our long vector right after the matrix. Now when I call display long vector, I would expect exactly the same output as when I call display matrix. So we can compare that in a moment. And let's just access one of the vector entries, let's say entry 6, and see what we get. So I would expect to get this entry here because this is the last entry of the matrix. So we're interested in this bit here now. This was our output for the matrix that we got here. And indeed, here's my long vector. Maybe let's output the whole matrix just for comparison. So we get the same output if we output the matrix and if we output our long vector. And indeed, the last entry in our long vector here, entry 6, corresponds to the last matrix entry we have here. So that works as we would expect it to. For the tables we have seen so far, the number of entries had to be known at compile time. So we gave them a fixed size in the working storage section. So the compiler would arrange for the memory to be precisely of the given size. But often we would like to build a table whose length is not known at compile time, but only determined at runtime. And to some extent, COBOL allows us to do this by using the occurs depending on clause. We see here in this example how it works. So we again have our matrix. Now I added 2 additional data items in the beginning, n rows and n columns, which means should be the number of rows and the number of columns. A 2-digit number, which I initialize with 1 just for simplicity. And now what I do is matrix row occurs 99 depending on n rows, and matrix column occurs 99 depending on n columns. So this works as follows. If I write occurs m depending on something, then m is the maximum number of entries in the table. So it's the maximum number of rows that I could require for a matrix here. And this has to be a constant. So I cannot have a variable here and have a variable size for my table. So even if I can have tables of variable length, we cannot have tables of arbitrary length, because the maximal length has to be defined when the program is written. We can also specify a range of allowed table lengths, so we don't just give the maximal table size, but also the minimal one. So to do that, we write occurs n to m depending on, and n, the first number, is the minimal number of entries, and m is the maximum number of entries. And these clauses depend on certain variables that we write here at the end. And these the length variables, can be contained, as is the case in the example, can be contained in the same record, but they could also be independent data items that we would declare outside of our matrix structure here and somewhere else in the program. Yeah, here I have my new matrix type with variable numbers of rows and columns. So as you can see here, I added the variables n rows and n columns to hold the number of rows and columns. And here's the modified matrix definition with the occurs depending on clause. What I will do now is I will read in from the standard input the number of rows and the number of columns for our matrix. And then I will just display the matrix of the given size now. And of course, since we initialize it with 0, we will just have a big lump of zeros on the screen. So yeah, we first build a 1-by-1 matrix because I initialized the rows and columns to 1. Now let's see, let's take a 4-by-6 matrix, 4 columns and 6 rows, and yeah, we rebuild our matrix as a 4-by-6 matrix. And you see here in the beginning, these two values are just the n rows and n cols variables, 4 and 6 respectively, and then we have all the entries 0 all written in a long string, because COBOL does not do any nice formatting unless we force it to do so. One thing we've just seen in the previous example is that we can change the length variable that determines the size of a table during the execution of the COBOL program. Now there are a few things to consider when doing that. So if by t we just denote any table of variable length, then according to IBM's COBOL programming guide, when we move t to another data structure, the length variable is queried just before the move to determine which size t has. So that means before moving t to another data structure, we must have set the value of the length variable at some point. And when moving data into t, we assume that the maximum size for t is assumed. So the length variable does not have to be initialized before moving data into t, unless we have the following situation. T is followed by a data item or record that is not subordinate to t. For example, if t itself is part of a record, and then that record contains more data items following t. So in that case, the size of t is determined just before the move, which would again require the length variable to be set. Now, this is all a bit murky from the programmer's point of view, so it depends on how the compiler does the memory management for your variable length tables and how this is all handled. But because you cannot really know what is going on under the hood, it is the programmer's responsibility to ensure that in any operation involving tables of variable length, all the operands have compatible sizes at the time the operation is performed. So COBOL is not shy about just overwriting stuff. Now here we have an example where we see this situation with data following a variable length table. So if we resize this table here, our matrix table, then you might suspect that when you increase the size of the variable length table t, that any subsequent data might be overwritten if we enlarge the table. So in this example here, that would affect first the trailing garbage and the after matrix data item. Now these two are different in the way that trailing garbage is contained in the same record matrix as our actual matrix data, whereas after matrix is just an independent data item that is declared just after the whole matrix record. As before, whether something like that can happen depends on how the compiler manages the memory. And what I found from experimenting with GnuCOBOL is that apparently it just, when it encounters a definition like this, it just reserves the maximal possible memory for this variable length table. So it would, in reserving the memory, just assume that we have 99 by 99 entries in our matrix and reserve that much memory for this whole matrix record. And because of that, this data item here after matrix would not be affected by any resizing of the matrix, because it is located after the maximal size of this whole record, so it could not be overwritten when we change the size of the matrix. But oddly enough, trailing garbage can be affected by resizing our matrix. So if we have a data item, let's say x, which could be in trailing garbage in the example. So if x is in the same record as our variable length table t, then it can be affected by changing the size of t. Because such a data item, x or trailing garbage here, is recorded by its position relative to t. So if we address trailing garbage, then COBOL will think, yeah, it's the next thing following at the end of matrix row, matrix column, and all that. So when the size of t changes, the position of x, of this trailing garbage, is taken relative to the new size of t. And therefore it refers to a different memory location than it did before. So be aware, resizing tables can have hard to predict effects on memory. And of course, what it does may differ between different compilers. So I'm just reporting what I experienced with GnuCOBOL. And therefore, I would recommend to just avoid having constructions of this type in GnuCOBOL or with any other COBOL compiler maybe. So if you have records of variable size, try to design your data structures in a way that you do not have any following data items in the same record. So here I've modified my data structure to include this trailing garbage in the same matrix record as my variable size table. And I also added this data item after matrix. And so that we can spot them more easily when we print out the matrix, I initialize them with some easy to spot values. And now I've already changed the whole program to be a bit more complex. So first, given that I initialized the number of rows and columns with 1, I will just print out this 1 by 1 matrix record, which in addition to the one matrix entry should print these two values here and the trailing garbage. And then I will have 3 times the possibility to read the number of rows and columns. And then I see what happens with the matrix if we enter different values to it. Well, interestingly enough, the trailing garbage was not even put out here. All we see is the 2 number rows, number columns, and the matrix entry. And the reason for that, I believe, is that GnuCOBOL probably reserved the maximal size for this whole table. So the actual location in memory where this WXYZ is located is at the end of a 99 by 99 matrix, which is not displayed here because we set rows and columns to 1, and when we call display matrix, it just uses these values to determine the size of the matrix. And so it just uses a tiny chunk of the memory that has been reserved for this whole record here. And yeah, there you already see a bit of an issue that you don't even see the value of this variable here when you have a different size than the maximal one. Now the next thing that happens is we read number of rows and columns. Let's say 2 columns and 1 row. And then we have a 2 by 1 matrix, so just a long, well, not a long, actually a short vector. And we move 1111.11 to the first matrix entry, and we move 999.999 to the last matrix entry. And we move XXXXX to trailing garbage. Now, we again print the matrix here, and we see this. So first, the first row entries, again, our number of columns, number of rows. Then we see the first matrix entry. Because we only have 2 entries in total, we immediately after that see the last matrix entry. And now we do see the trailing garbage, because now trailing garbage is taken relative to the new size of the matrix. And it points to the proper position. Okay, now let's change the size. Let's say we do 20 by 20. I did not change the value of trailing garbage now. I did not change any other entry in the matrix. So what we see is we still have the entries that we had before. Trailing garbage is now part of the matrix. It's not at the end of the matrix as it probably should be, because that is the value we assigned to it before resizing the matrix. It is now actually the third entry in the matrix. And if we print trailing garbage now, we get zeros, because now we again take trailing garbage relative to the resized matrix. So it would point somewhere here at the end. And that's just some chunk of memory that has been initialized with 0. So trailing garbage is now 0. And so we see resizing the matrix has a very disruptive effect on a variable in the same record that follows this variable length table. And now we do the whole thing once more. Let's make the matrix a bit smaller again, now one by one. So we have a really tiny matrix now, again with the data that we put into it originally, even though now there are 2 decimal points missing here. And trailing garbage now actually points to this value here, because we shrunk this matrix to the point where it contains only 1 entry, so that would be the one with the ones. And trailing garbage now are the 4 characters immediately following this 1 entry, and those would be the 4 9s here, because that is what we assigned to it originally at the beginning. Yeah, so you see resizing is a bit problematic, and but what we do see is after matrix, the data item that was declared after our matrix table, that always has consistently the same value. So this one is not overwritten, and as I said before, I suspect that is because the compiler reserves the maximal possible memory for this bit, and only then does it reserve memory for after matrix. And that's why after matrix is not affected by resizing the table here. And that's it for tables. Now we want to have a look at how we can modify data structures in COBOL in order for them to be printed in a more readable format. What we've already observed, especially with our matrix table in the previous examples, is that when we just use the display instruction on a COBOL record or a table, it just dumps all the data items contained in the record in a continuous and unformatted stream of characters. Now, this, of course, makes the output practically unreadable. But there's one nice feature in COBOL that allows us to include formatting information within the definition of the records themselves. And the way to do this is to use so-called filler items, which are data items that can be included in the record that are never referenced, but contain some constant values that are printed when the record containing them is displayed. And because we don't reference them, they don't need a name. So instead of giving them a name, we just use the keyword filler. So for example, ways to use this would be to include spaces or bars to separate data items, or we could use strings as fillers that provide additional information about the data that is being output, or we could use special characters like, for example, hex 0a to get line breaks in the output. Now, one downside of this is that all of these filler items do actually take up memory in the data structure. So it's not like we're writing a procedure here that outputs the data in a nice way, but it's actually additional data that is written to memory. Here we have a big example of that. So again, this is the personnel record that we had before with Homer Simpson and his address in it. And to sort of mirror this plain personnel record, I have what I call a pretty personnel record. So it's the same data, but with fillers to make the output more appealing. So you see here we have filler for a line break. Then we have filler for the string full name. And after that, we have first name, last name. Then we have again filler for a line break, the filler for the string address, and so on. We have a comma that separates street and city. Then we have department, and then we have salary. Before we see how that works, there's one additional thing we should make use of. So, as we've seen in this previous example, one option to obtain formatted output of a complex record is to have the lightweight data structure, so the plain personnel record in the previous example, that just contains the data that we need for processing. And then to mirror that, we have another data structure with additional fillers to format the output nicely. We have these two data structures with corresponding entries, and those corresponding entries in the example had identical names. And because they have identical names, we can use a convenient COBOL operation to move data from the first record to the second one with just one single command. And that is move corresponding personnel record to pretty personnel record. So what this would do, it would take any data item in the personnel record and move its value to the data item of the same name in pretty personnel record. Unfortunately, this is not practical when using tables, because we cannot access table entries in conjunction with the in and off keyword. So if we have these lightweight data structure and the corresponding pretty print data structure, and their record entries would have identical names, then we would have to use in and off or off keywords to resolve the ambiguity in the naming of these data items, and that does not work with tables. Therefore, we cannot have multiple tables with the identically named entries if we ever want to access them by subscripts or indices. So we cannot use move corresponding here. So when we have a separate data structure for pretty printing tables, we must use unambiguous names for the entries and copy them one by one from the original table, unfortunately. Here we have our pretty print program. So again, our plain personnel record, the lightweight data structure, if you like. And here we have the inflated version of that for the pretty print. And you see it has the same data items with the same name as this one here. And in addition, all these filler items. Now let's see how we can use that. So what we do, we use the move corresponding from personnel record to the pretty personnel record. And that should move the value Homer to the first name here, the value Simpson to the last name here, 742 Evergreen Terrace to the street here, and so on for the other entries, and all just in this convenient single line. Let's display this. So first we do the ordinary print of the plain data structure. And then we print the nicely formatted one. With our pretty personnel record. And let's see how this looks. Yeah, so here we have the shitty print. Let's make the terminal a bit bigger, where everything is just dumped on one line. It is readable enough, but rather ugly. And here we have the pretty print, which could still be better, but it's already much nicer. So we have the additional strings here to identify what data we're actually looking at. We have Homer Simpson on one line as the full name. Now these spaces here, of course, due to the fact that these are 20 character variables, so all the 20 characters are printed, but if they're not occupied by any value, we just get a blank. And it's the same for the address with the street name and the city. We have the comma here from the filler, this one that nicely separates them. And finally we have the salary again. There are a few digits that are 0 that are not printed here but are still output as blanks, so that's why we get the weird indentation here. And I also want to show you how we can pretty print a 3x2 matrix that we had before. I just now copied this in here. So here we have a 3x2 matrix. I do not do this as a variable length table. I will explain that in a moment, why that doesn't really work. So it's just a fixed size 3x2 matrix. And here we have the pretty print version of that. So I start again with a line break. And then I have all of these things to format it in a nice matrix notation, which is of course adapted to the fixed size of 3x2. And as I said, unfortunately it wouldn't really work for a arbitrary length matrix. So here I have some bracket-y thing on top of the matrix, a line break. Then these bars to make up parentheses for opening the matrix, a few spaces, and then the actual matrix entries. And then again these brackety things to have the matrix closed at the bottom. And this is what I will do with the matrix. So I just move some values to the matrix entries, just these fractions to easily identify which row and column we're in. Then one by one I move these matrix entries into the pretty print matrix. So as I explained before, it's unfortunately not feasible to use this move corresponding with tables. And then I will print the two matrices and see what I get. Here again we have our Homer Simpson twice, and now we have the matrix below that. First the shitty print where everything is just dumped on one line. And here we have the pretty print, and we can see it really makes a difference to introduce these fillers into the data structure. So here we have a nice matrix notation with conveniently spaced entries. And I already hinted at it before that I said I just chose a fixed size matrix because the whole filler thing doesn't really work with variable length tables. And the reason for that is when we change the size of a variable length table, then we will overwrite any subsequent data items contained in the same record as this table. And this also applies to filler entries. So changing the size of a table will destroy the formatting information provided by the fillers, and on the other hand might cause the filler data to be written to some of your matrix entries when you change the size. So this is not something you would want to use. If you're keen, you can try it out in GnuCOBOL and see what it does. I've done it, and it doesn't work at all. So unfortunately fillers only make sense with records or tables of fixed size. And if we actually do want to do formatting for variable length tables or records, then the best is probably to just write a procedure to format it for display. And we haven't talked about procedures yet, so that's something for a coming chapter, but we will just leave it at that now. In the last two sections of this chapter, I want to talk about the basic built-in operations for arithmetic and for string variables in COBOL. So we begin with the arithmetic. And first, let's talk about the way that COBOL stores arithmetic variables. So traditionally, COBOL uses binary coded decimals, also called BCDs for short. And these correspond to the usage computational 3, or the packed decimal, which is equivalent to comp3. The arithmetic used for these is known as fixed point arithmetic. And in this representation, each byte encodes 2 decimal digits. So we have 4 bits per digit. And for signed numbers, the highest order byte contains 1 digit and the sign. So we use 4 bits just to represent the sign of such a number. In later COBOL standards, there were also floating point numbers introduced, which are maybe a bit more modern and maybe a bit more complicated to understand than the BCDs. They correspond to usage comp1 and comp2, so this would be 4 bytes or 8 bytes, which would correspond to float and double in the C-like languages. Floating point numbers are a binary format. That means their bits directly encode the binary representation of a number, and additional bits encode the sign and an exponent for that number. Floating point arithmetic is usually considered to be more efficient than fixed point arithmetic because we can store a much larger range of values in a given amount of memory, and there are very fast hardware implementations for floating point arithmetic, the so-called floating point units, FPUs. A downside is that we cannot represent every rational number within the range of a given floating point representation. Now, the IBM standard specifies that COBOL defaults to fixed point arithmetic unless one of the operands is a floating point number or an exponent in the computation is a fraction. In that case, it will switch to floating point numbers. And I suppose you can imagine that mixing fixed and floating point arithmetic is particularly inefficient because you have to convert the operands to floating point numbers every time. So if you plan on using floating point numbers, it's probably best to just make sure that all of your variables that you do computations with are floating point numbers. In financial applications, fixed point decimals are often preferred, at least were often preferred in COBOL times, as the precision of these calculations can be controlled through the number of decimal positions that we specify for the binary coded decimal representation. But on the internet you can find lengthy debates on the advantages and disadvantages of fixed point versus floating point numbers. I don't want to get into that here, but you can Google it for your entertainment. As always, COBOL tries to stay as close to written English as possible, and it even does that in its arithmetic operations, which can make them quite cumbersome if you use addition, subtraction, multiplication, and division, because these operations are actually supposed to be spelled out in words rather than using the common mathematical symbols. So let me show you that. X, Y, Z should represent arithmetic data items or constant numerals in the following. And in addition, X plus Y equal to Z can be expressed in COBOL as add X to Y giving Z. That's self-explanatory, but it's very wordy and much longer than just writing down a formula like this. Similar, a subtraction X minus Y equal to Z will be expressed as subtract Y from X giving Z. A multiplication, X times Y equals Z, is multiply X by Y giving Z. So all self-explanatory but very verbose. And a division, X divided by Y equal to Z, is written as divide X by Y giving Z. Or there's an alternative way, which I find very confusing. This is divide Y into X giving Z. So here we reverse the order of X and Y. And yeah, I can't really make sense of this expression here, but you can use it. I would not recommend it because I find it very confusing. And this one, on the other hand, seems pretty straightforward. You can follow the divide operation by a remainder r, which saves the remainder of the division in a variable r. And we can apply add and subtract to records with some identically named entries using the corresponding keyword, similar to what we did with the move instruction. So recall that when we had move corresponding, all the values from the first record were moved to the corresponding values, so the entries with the same name in the second record. And in a similar way, we can use add or subtract with the corresponding clause to add or subtract the respective entries with the same name from the two records. Now, if the target variable z in these operations here does not have enough decimal positions to properly contain the results of any of the operations above, then we will simply truncate the default to fit into z. So we will just cut off the decimal positions. And instead we can use the keyword rounded if we want to round up or down, depending on what the value is, to the last decimal position of z. So in that way, using rounded, you might get a little bit more precise results. COBOL does provide some simple exception handling methods for its arithmetic operations. If an overflow occurs because the target variable z has too few digits to contain the result, so z is too small to contain the result, then COBOL will actually do nothing. It simply fills up z with as many digits as it can contain, and all the higher order digits will be lost. So for all intents and purposes, we may assume that the result is useless then. Garbage. So we can remedy this by following the arithmetic operation by an instruction on size error C, where C stands for some COBOL instruction. So this would be our exception handling instruction for the situation that an overflow occurs. For example, it could print an error message, or it could branch to some other part of the code to handle the overflow error. And oddly enough, we also have an exception handling for the situation that no exception occurs. So the arithmetic operation can be followed by a not on size error, D, and then another instruction, D, would be executed in that case. Maybe there are situations where this might be useful, I don't know, but it's a funny idea to have an exception for the case that no exception occurs. And here I have an example with some arithmetic variables to play around with. So we begin with int1 and int2. These are binary variables. Then pint, so the p here stands for print, so this is what I want to use to print the result in a readable manner. R stands for remainder, and these are defined as usage display. And I also have two fixed point arithmetic numbers, fix1 and fix2, which are defined by usage comp3. And again, pfix, this will hold the result of the operations I do with these, which is defined to be usage display. Now, first what I do, I assign some values to my fixed point numbers, some fractions here, and then I will add one to the other and print out the result. And then I will multiply them, where I implement an error handling here for the situation that the result becomes too large. And if nothing happens here, I will also print the result. Actually, I will print the result either way. And yeah, similarly with the integers, what I do is I move some values to my integer variables. Then I divide one integer by the others, given the integer quotient of those. And I store the remainder in R. And then I print out the two results here. So let's do this. and we have an error. Binary fields may not be larger than 18 digits. That's funny. They must have introduced that in the latest version. Of GnuCOBOL. Now it works, so we see fixed point numbers actually are allowed to be more than 18 digits, but binary numbers are not. Let's see actually if usage is display. I guess I might have a larger value as well. Yeah, that's allowed too, so quite interesting. All right, what do we see here? Here's the result of adding the two fixed point numbers, these two values here. Then the result of multiplying them. And down here we have the result of our integer division, which is just 6. So it's the rounded quotient because 6 times 4 is 24, so 4 fits 6 times into 25, and as a remainder we have 1. If you look at these 4 modes of performing basic arithmetic operation, then it might seem like a nightmare to have to process more complex arithmetic expressions in COBOL. But luckily, COBOL does provide a compute instruction that allows us to write out a sequence of operations as a regular mathematical formula. And I suppose this is, in most cases, preferable to using the verbose version of the arithmetic operations. Now the syntax is compute z equal to a, where z is some arithmetic data item, and a is any arithmetic expression involving variables, constants, and these operators here, which would be addition, subtraction, multiplication, the double star for taking exponents, and division. And of course we can use parentheses to group sub-expressions. Now we have an example here. I define 4 fixed point variables and move some arbitrary values to them, and then I just perform this computation here involving subtraction, exponentiation, and division. Let's see how that works out in COBOL. So we just copy these variables in here, and then we perform some operations with them. We move the value 3 to x, we move the value 192 to y, we move 23 to w, and then we compute z equal to y minus x squared, and the whole thing is divided by 2. And we display this as a for arithmetic expression. So here we have the result of our expression, so we can nicely evaluate all these operations in one go using the compute instruction. The result we get is 1552.17. That is not very precise, to be honest. The proper result should be something like 1503.1-ish. So yeah, maybe if we give a few more decimal places to z, the result will get better. And oddly enough, it gets much, much worse. So I don't really know what's happening here, but this is completely off. By giving 4 decimal places. Let's see what happens if we put in some more. Yeah, that's very interesting. I do not understand what is happening here. Maybe if one of you understands it, you could explain it in the comments. Maybe things get better if we just use 1 decimal position. Yeah, that's closer to what we should have. So this is actually the best result so far with the lowest precision. If we remove the decimal point, that has the same effect. So yeah, I'm quite confused about this. I honestly don't really know how this happens, but it's definitely not good. And as I said, maybe if someone who's watching this can explain it, please write it in the comments. When we use the compute instruction, we have to be aware of the priorities that the different arithmetic operators have. And this is the table of the priorities in such expressions. So the highest priority 1 is given to signs. So if we use plus or minus as a sign in front of a variable or a constant, then this has the highest priority. The next highest priority is given to the power operator, the double star. So if we exponentiate a value by another one. Third highest priority is given to multiplication and division. And fourth highest priority is given to addition and subtraction. So it's basically what you know from school already. And as an example, we have this arithmetic expression here, a plus b times c minus d taken to the power of e taken to the power of f plus g times h. And this will be evaluated as follows if we use the parentheses to indicate what is done first. So the first thing that would happen is we take e to the power of f, then d to the power of e to the power of f, we multiply b by c and g by h, then we add a plus this part, subtract our double exponent, and finally add g times h. Again, this is probably familiar to you, not too surprising. This is exactly how you would have done it in school. COBOL also has some built-in mathematical functions that we could use within a compute expression. Just some examples here. You can compute roots, and this you can actually do by simply using the exponentiation operator with a fraction. So to compute the square root of x, you could write x to the power of 1/2. You can use exponential functions and logarithms by calling exp and log. Or if you want to use base 10, write exp 10 and log 10. So these ones would be the natural logarithm and the exponential function with the Euler number. You have trigonometric functions, sine, cosine, tangents, and their inverse functions. You have maximum and minimum functions for a set of numbers. You can compute certain statistical quantities such as mean, median, variance, standard deviation. And you can generate random numbers using the random function. And there are many, many more built-in functions, and you should check out IBM's COBOL programming guide to see which one there are. And to use such a function, let's say call it f for any of these functions here. Well, other than the roots, which you can just write like this, but if you use any of these other built-in functions within the compute, you have to preface it by the function keyword. So you would write something like compute z equal to function, and then f, which is any of the functions mentioned here, followed by the list of its arguments. Now we look at the built-in operations for strings in COBOL. So there are several built-in operations for manipulating strings, and by a string I mean any data item that is defined via pick A or pick X, or the numerical types defined with usage display. The operations that COBOL provides involve counting characters in strings, replacing characters in strings, splitting and concatenating strings, and accessing substrings. We start with COBOL's inspect instruction, which is quite a multi-purpose instruction because it allows us to count characters in strings and replace characters in strings in several different ways. First, to count all characters in a string, which we call capital S here, use the command inspect as tallying counter for characters. So counter here is a numerical variable of display type, and this will take the number of characters that are contained in the string S. And the for characters simply means that all characters should be counted. One important thing to understand here is that when we use this tallying counter keyword, the counter is not initialized to 0, but rather we add the number of characters in S to the previous value of counter. So if you just want to count the characters contained in S, you have to make sure that your counting variable is set to 0 beforehand. There are two variations of these instructions that allow us to only count certain characters or substrings in our string, and I use the lowercase s for the characters or substrings. We can do this using inspect s, tallying counter for all lowercase s. Then we would count all occurrences of this substring here in the string capital S. And we can count all the occurrences of our substring within our string S under the condition that S begins with the substring lowercase s. And for this we use the command inspect s, tallying counter for leading lowercase s. It's quite a particular command, but well, can't hurt to have it. We can further refine this counting method by using certain keywords, namely the before and after keyword in the inspect instruction. So the before keyword following the inspect instruction means that inspect is only applied to our string up to the first occurrence of the character C or the substring C within S. And naturally then the inspect instruction followed by after C means that inspect is only applied after the first occurrence of the character or substring C within our string S. You can combine these two commands, so with different characters or substrings for each, of course. And you can also combine them with all the previous version of the counting instruction. Here I prepared a program to try out the string instructions. So first I define a string, which is just called string1, maximal 20 characters and initialized with hello world. And I define a counter variable, which I initialize with value 0. And in the procedure division, we have different counting commands. So we begin by counting the total number of characters in our string. So we use the command inspect string1, tallying counter for characters, and recall that for characters here means that we count all the characters contained in our hello world string. Next, I want to count the occurrences of the letter O. So we should have two of them, one in hello, one in world. First, I reset my counter to 0, and then I use inspect string tallying counter for all character O. Next up, I use one of these particular counting commands I want to count the occurrences of the letter capital H if the string begins with the capital H, which is the case from hello here. So we would expect to get one character counted. So again, I reset my counter to 0 and then use the command inspect string 1 tallying counter for leading character H. And then I do the same thing with the character X, which is not contained in the string, so I would expect to get a count of 0 here. I initialize my counter to 0, then I use the inspect string tallying counter for leading character X, and I display it. And finally, I use one of the more complex counting instructions. I reset my counter to 0, and then I want to count all the characters in the string following the initial string hello. So I use inspect string tallying counter for characters after hello. We compile and then the total number of characters is output to be 20. If we compare this to our hello world string, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters, that is of course nonsense. So apparently, if we count all characters, the inspect instruction just counts the whole number of characters that are reserved for our string. So we initialized it to be of size 20 and it just gives us back size 20. That is absolutely not helpful, and I would venture a guess that this is an implementation bug in GnuCOBOL rather than intended behavior. Anyway, we're better off with counting the letters O. So hello world contains 2 letters O, and indeed we get a count of 2. And also the next one is spot on. The character H, if the first character is H, is counted to occur once, which is true, the capital H from hello. The letter X does not occur in our string, so we get a count of 0. And again, characters following hello gives us a count of 15, which is nonsense because it's more characters than our string even has. So again, here we count all the characters that have been reserved for our string 1 minus the characters that were used up for the string hello. So this is a bit annoying to have this behavior, but it is what it is. We can also use the inspect instruction to replace any occurrence of a character or a substring in a given string. So again, our character or substring is a lowercase s, our string will be a capital S, and we can replace it by a given character or string C using the instruction inspect s, replacing all lowercase s by lowercase c, with the restriction that s and c must have the same number of characters. So we can only replace substrings by other substrings of the same length. And the result of the replacement is written to s itself, so it's not stored in some third string that we're given, but it's done in place. Here again, we can apply some modifiers to the replacement instruction. So we can only replace the first occurrence of our substring lowercase s by writing inspect s replacing first s by c. And we can also choose to only replace occurrences of our substring s if our main string capital S actually begins with this substring. For this we use inspect s replacing leading lowercase s by c. And just like we did with inspect tallying, we can use the keywords before and after in the replacement operation. And if we just want to set all the characters in a string to one given character, we can use the following: inspect s replacing characters by c, so that will take any character contained in our string and replace it by the character c. We can combine the counting and replacing in the inspect instruction, so we can use both telling and replacing simultaneously in one single instruction. And this can be combined with all the options for telling and replacing that we previously discussed. One restriction is that the telling command must appear before the replacing. And for example, we could have something like this: inspect S telling counter for characters replacing S by C. So we count all the characters in S and replace a substring lowercase s by a substring C. The counting is done before we make the replacements, but it shouldn't make a difference because S and C must have the same number of characters anyway. But for readability, it is probably better to separate telling and replacing instructions in separate commands. So already this gets a bit long, and if you use some of the additional options, I think it gets rather confusing. Here I copied in some commands to replace substrings in our hello world string. Namely, what I will do is I will translate our string into German. The first command will replace all occurrences of the word hello by the German spelling hallo. And the second command will replace any occurrence of the English word world by the German word Welt. Because world and Welt do not have exactly the same number of characters, I added an extra space in front of Welt, so that will make it look a bit weird, but it will be correct. And then I will output the German version of hello world. And here I will try a brutal replacement of all the characters in string 1 by a hash symbol, and this will completely obliterate any information contained in our string. And here we are replacing, so we translate hello world into German and we get hallo Welt. The exclamation mark remained from the English version, and you see, we have two spaces here now because, as I said before, world has one character more than Welt, so I had to add an additional space to get a correct replacement. And here we just overrode every character in our string 1 by a hash sign, and nothing is left of any information previously contained in it. Another thing we can do with the inspect instruction is to convert characters in a string that belong to one given set C1 to characters contained in another set C2. And these two sets must have the same number of characters. We will give them in COBOL in the form of a string where we just list the characters one after another. And we then say the ith character of C1 corresponds to the ith character of C2. And the instruction to do this is inspect S, converting C1 to C2. Again, the result is written directly to S. And we can also again use modifiers before and after to restrict where the instruction should apply to in our string S. Here is an example how we could use this to convert lowercase to uppercase letters, or vice versa if you like. So in the working storage section, here's my string that I defined before, and now I define these two sets C1 and C2 as the uppercase and lowercase letters, and I simply list them all one after another in a string, and so it's clear to see which one corresponds to which. Each uppercase letter corresponds to its lowercase version. And then in the procedure division, we could use this with the instruction inspect string 1, converting lowercase to uppercase. Let's see this. Here I have my replacement sets defined as COBOL variables, uppercase, containing all the uppercase letters, lowercase containing all the lowercase letters, and just for the fun of it, I defined a rot13 variable, which is a replacement of all the characters in the alphabet by the character that we get when we rotate the alphabet by 13 characters. So this is a very crude encryption method that is sometimes used for demonstration purposes. So let's look at the code. I have a string 2 that I have not defined yet, so let's include a string 2 in our definition up here. And now our string 2 containing the value goodbye world will be converted from lowercase to uppercase. We print this, then we do the reverse. We convert it from uppercase to lowercase, and then we apply the rot13 transformation on string 2 and see how it will look then. As we expect, the uppercase version of string 2 is goodbye world, all in uppercase. Then we have the lowercase version here. And if we apply the rot13 transformation to goodbye world, we get the string COBOL. We can also concatenate several strings in COBOL. This we do not do with the inspect instruction, but we do this with the string instruction. So if we're given several input strings, S1, S2, blah, 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 and so on, we can concatenate them to give a target string variable, which I call T, by writing string S1, S2, and so on into T. We can use the keyword delimited by D, where D is some delimiter substring. After any of those input strings here, and that allows us to only concatenate these strings up to the first occurrence of the delimiter D. So this would look like here. String S1, S2 delimited by D, S3, S4, blah, 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 into T. What this does is that S1 and S2 are delimited by D, so only up to substring D we take those and concatenate them. And all the strings that come later are fully included into the resulting string T. We can also use the keyword pointer counter with a counter variable here. That allows us to specify the position where the concatenated strings should be inserted in T. So counter points to a position in our target string T, and at that position we will write all the concatenated strings here. Now note that for counter you have to use a numerical variable. You cannot give this value as a constant here. And again, we allow exception handling here, similar to the arithmetic operations. We can use an instruction or a clause on overflow C at the end of this string instruction, and this command C will then be executed if the target string T is actually too small to contain all of the concatenated strings here. And again, we have this non-exception handling, the not on overflow instruction, which can be executed if no overflow occurs. We can also split a string into substrings. So given a string T, we can split it into substrings S1, S2, and so on, using the unstring instruction. And we can use the keyword delimited by D1 or D2 or and so on to give a list of delimiting characters, D1, D2, and so on, at whose occurrence we split the string. So think of punctuation signs or spaces or bars or something like that. This would look like this: unstring T delimited by D1 or D2 or into S1, S2, and so on. Now, what is a bit tricky here, that is you actually have to have enough strings in the back here to take in all the parts that T gets split up into. And of course, if t is something that's dynamically generated, it might be hard to predict beforehand how many strings you need to have here. So maybe it's best to define a few strings in reserve and make an educated guess about how many you will have to use for splitting up t. We can additionally use by all instead of by, and or all instead of or here, to treat multiple consecutive occurrences of a delimiter as one. For example, if you have a text and you want to split it up into individual words, but several words could be separated by more than one space, then you could use by all and or all to count several occurrences of a space character as just one. You can further count the length of the substrings that are generated here by using the keyword count in countJ. So here we have a counter variable for each of these partial strings here, and they will take the length of the corresponding string that is generated by splitting up t. And similar to what we could do with a string instruction, we can provide a counter variable as a pointer. So we use pointer counter to indicate at which position in our string t we start the splitting. We can use the keyword telling counter to count into how many substrings t will get split in this command. And again, we can use an onOverflow exception handler to execute a COBOL command if any of the substrings given in the back here is too short to contain the jth substring that t split up into. To see concatenating and splitting in COBOL, I introduce a few new variables. So here I have long string, which is indeed a long string, which I want to use to concatenate certain strings into. Then I have the string split me, which is a line containing several words separated by spaces and a comma. And here I just have a few strings of length 10 characters that I want to use to take up substrings of this string split me. Down here I have some test code. First I want to concatenate. I move 20 to my counter variable, and then I use string 1, string 2 into long string with pointer counter. So I want to start at position 20 in long string, and then I want to concatenate string 1 and string 2 into long string. So at this point, string 1 should actually be the string that is overwritten by all hash characters, and string 2 should be the ROT 13th version of goodbye world. So this will look quite weird. And the rest of long string contains only periods to indicate the positions where the characters are, and to make it easier to spot where we inserted those two concatenated strings. Then we will move a single space to long string and just concatenate string 1, string 2, delimited by a space into long string. Finally, we do the splitting. We take the string split me, which contains a line from Hamlet, delimited by comma or space, and we split it into these 6 empty strings that we defined above, and then we print out all the individual parts. So what happens here? We count, we replace. So this is our string 1 now, after this command. This is our string 2 now, after this command. And indeed, when we concatenate them here, we concatenate them at position 20 in our string. So here's string 1, and it's immediately followed by string 2. Then, next what we do, we partially concatenate them, but we use delimited by a space. So because string 2, this string now contains a space, we only concatenate string 2 up, only this part of string 2 up to the first occurrence of a space. So what we get is indeed this string here. And then we take the line here, the tragedy of Hamlet, Prince of Denmark, and split it into substrings delimited by comma or space. So we get the individual words, the tragedy of Hamlet, Prince, and so on. So we don't have enough variables to take in all the words. But if we had 2 more splitting variables, we would see of Denmark here as well. Finally, we want to see how we can access substrings of a string. So again, we're given a string S and we want to obtain a substring as prime by providing the index of the first element of S prime in S and the desired length of S prime. And for this we use the notation S parenthesis I colon L. So here I is the starting index, so where S prime begins, and L is the length of S prime. And these characters are extracted from the string S and give our substring S prime. And both the index and the length can be given as variables or as constants. Here we have an example for that. Again, we have our string with the value, the tragedy of Hamlet, Prince of Denmark. We move 8 to the counter variable and then we take the string name, string 2 in this case, beginning at position 4 with the length counter, so 8 in this case, and we write the result to string 1. And I do this here, I move 8 to the counter variable, then I take the string split me, which was our line from Hamlet, beginning at index 4, 8 characters long, and take the resulting substring and move it to string 1, and then I print it here. And what we get is this output here. We get the word tragedy. This string is actually 8 characters long, so it begins with the 4th character, which is a space following the word the. And then we have the 7 characters from the word tragedy. So these are characters 4 to 12 from our string. And that's it. We're at the end of our chapter 2 on data structures and data items in COBOL. Thank you very much for making it to the end, and do not forget to like this video and subscribe to my channel.